Okay, so today we'll finish up Proton NMR and get into the next NMR, which is C14. So let's finish up Proton NMR by looking at a couple more examples. Let's suppose we wanted to analyze the NMR for this molecule. Remember, that's called para-toluene. Okay. So again, when you see the benzene molecule, make sure you show the hydrogens that are there. Okay, so we get 4 hydrogens. Okay. Now we want to show the NMR for this. Okay. So what's the first question we ask once again? How many peaks or the number of signals? Okay. And to determine that, we use what? What tool do we use?
Plane of symmetry.
The plane of symmetry. Okay. So does this molecule have a plane of symmetry?
Yes.
Yeah, it has one right here, right down the middle. Okay. So right there. Okay, so that makes those hydrogens there the same. Is there any other planes of symmetry? Straight across. So that makes what? These hydrogens the same. And these the same. Okay? So all 4 of those hydrogens are the same. Okay? What about those 2 CH3s? Are they the same? Are they the same? Yeah, through this plane of symmetry. Okay? So this one makes those 2 CH3s the same. So we can call those B. Okay? So you see how this one differs from the one we did last time. This is para-substitution. Okay? But the para-substitution we did last time, we had 2 different groups. Okay? And so that threw off the symmetry going that way. But now when the 2 groups are the same, we get that extra symmetry, so it's going to condense our number of peaks. So we get 2 different peaks, A and B. Which of those 2 peaks, A or B, will be more downfield?
A.
The A, because it's right on the benzene. And B will be more upfield, okay, CH3s. What will the B signal look like? Well, hold on, question.
So you said A would be more downfield because it's right on the benzene.
Right.
So that rule don't apply to the ones with the 3 hydrogens or less?
No. No, these are benzene hydrogens. Benzene hydrogens always show between 7 and 8. Okay, CH3s, CH2s, and even regular CHs, they always show more upfield. Okay, so 7 and 8 benzene hydrogens, so that's where we're aiming at there. Okay. So back to B, what will the signal look like for B? A doublet, singlet, triplet? What will it look like?
A singlet, right?
Yeah, that's right. There's no hydrogen there, is there? So N is 0. So B will look like a singlet. And And that will represent how many hydrogens? 6 hydrogens. Okay. What about the A signal? What will A look like?
Doublet, no, a single, nope.
That's right, you would have predicted maybe a doublet, but that's the same hydrogen now.
Singlet.
And remember, same, don't split the same.
Yeah.
So it'll be a long singlet. Representing 4 hydrogens. Okay, so it won't be as tall as this singlet, that you get 2 singlets. And of course, this one will be between 7 and 8 on the chemical shift. Okay, this singlet here is probably showing up at around 2. Okay, as you've been reading, CH3s by themselves with no deshielders usually show up at 1 or less. As soon as you start putting a deshielder next to CH3s, they start going higher downfield from 1. Okay? So the more deshielders you would have, it would even get higher, you know, given like some of the examples we saw last time. Okay? So any questions on how we did this one here? Okay? Hopefully it's starting to make a little bit more sense. You see how you have to use those 3 rules. Okay? Use them over and over so you don't miss anything. Okay?
I have a general question.
Sure.
Like when we have a lot of different groups, so we have like A through E or something like that, and like say we have 2 para groups, and one of them has a deshielder within it, like a carbonyl group, and then the other one may not. How do we determine like which one's gonna be more downfield? Because the benzene ring makes stuff more downfield, but then so does a carbonyl. So then how do I know like which one is more?
Yeah, usually the carbonyl is a stronger deshielder than the benzene ring. Okay? So if you were gonna maybe try to get a gauge of things, carbonyl is usually stronger than a benzene ring. Okay, and then you'll have other electronegative atoms like oxygen or chlorine and so on. And those tend to be somewhere in between those, okay? If you read the book, it'll give you the exact values, okay? That I won't force you to memorize. All I'm going to be looking for on the exam are, can you position them? And I'm not going to give you tricky, you know, which is more downfield, one next to a chlorine or one next to the benzene. They'll be obvious, you know, as to what to do there. Okay. But, you know, if you had a molecule like this here, okay, you should be able to predict that this hydrogen will be more downfield than that one, right? Because I got 2 chlorines compared to 1. So that's one. Okay. Any other questions? Okay, let's look at another example here. Again, you need to make sure you're drilling yourself through the homework problems. Let's look at this one here. Okay. So here, obviously, there's no plane of symmetry, so we get 2 peaks. Okay. And which of those 2 peaks should be much more downfield than the other? Okay, the B. Okay. In fact, what kind of peak is B? That's the, yeah, it's a singlet. That's a carboxylic acid. okay? And remember, those show up at around 15 or so, okay? 12 to 15. So those are your most downfield peaks that you could have, okay? And then A would look like what? A singlet that would be 3 times as tall as the B, because you got 3 hydrogens. Okay. Questions on that simple one? Okay, I wanted to show you what a carboxylic acid looked like. Okay, so make sure you're drilling yourself on these kinds of things, okay? Want you to make sure you're going through the chapter and look at the spectra that they did for you and they labeled for you, and make sure you can see why those hydrogens match those particular peaks, okay? Make sure those are clear to you. Homework problems like the one on page 579, okay, where they give you different molecules and different NMRs, and they tell you to match the molecule with the NMR. Make sure you can do that, okay? So always use those 3 rules, okay? And when the exam comes up, as soon as we get the exam, I write down the 3 rules to make sure I follow them, you see. You might say, when is that next exam coming up? Okay? We're probably looking at next Wednesday. Okay, so right around the corner. So we'll be finishing things up next lecture on Friday. Okay, one other topic before we move on to C13 NMR. Okay, that's the topic of the coupling constant. Okay, coupling constant, and that is usually given the symbol J. Okay, let's figure out what the coupling constant is, and let's do that by looking at our old friend chloroethane. Remember our friend? Our friend now should be very friendly. You should be able to draw that spectrum very quickly, shouldn't you? Okay? What does the spectrum look like? Well, again, very quickly, we have 2 sets of hydrogens. Maybe call this A and this one B. Okay? So, which of those 2 will be more downfield? The B. Hope I did not hear someone say A. Okay. So B, more downfield, what will B look like?
Quartet.
Quartet, so we're still not quite there yet, some of you. Okay. I shouldn't have heard any mistakes on this one. I should not have heard any mistakes, and I've heard 2 so far. Okay, so the B be more downfield, so a quartet, and then the A would be more upfield as a triplet. Okay, any questions on our old friend? Okay, we're going to look at our friend from a different angle now. What we can do is go in between the splitting here and measure the distance of those splitted peaks, okay? And that distance is going to be measured in hertz, okay? And let's say that that distance, we'll just pick a number. Let's say it turned out to be 7 hertz, okay? So it's not measured in centimeters or meters, it's measured in hertz. Well, that distance is what's called our coupling constant, J. Okay? So this is a way that we can further analyze the peak and report the peak by reporting what its coupling constant is. Okay? Just some extra detail. You might say, what benefit can we get from that extra detail? Here's the benefit. If you were to measure the distance between these peaks, you would get its J value. And here's the benefit, that if we have two sets of hydrogens that are splitting each other, they will have the same coupling constant. They will have the same J value. So what do you think the J value of this one here would be? 7. 7 hertz.
You said the same with 2 sets of hydrogen? What'd you say?
Okay. So 2 sets of hydrogens that are splitting each other will have the same J value. Okay? So that's nice to know. You know, no big deal here. That's a simple molecule. But if I had a complicated big molecule where I had lots of hydrogens and lots of peaks, you see how that could be helpful? I could then say, okay, those 2 particular peaks had the same coupling constant, so they must be splitting each other, or those hydrogens must be next to those hydrogens representing those peaks. Yeah, I'd give it to you. Yeah. I'd give it to you. But in reality, you would measure them. Used to be the way you measure them is you pulled out a ruler and measured it. But now you can do it on the NMR machine. It will give that to you, so it's pretty easy. And so I'll be easy to give it to you as well. Okay? Okay, so that's all the coupling constant is. The way that you'll see these labeled is this one here is the coupling constant for the A peak, right? But that A peak is being split by the B peak, and so we will call that one JAB. What do you think this J would be called? JVA. Okay, so the first letter represents the peak, and the second letter represents what it's being split by. Okay. Questions on that? Okay, so that's the end of Proton NMR. Okay, again, I can't stress the importance of drilling yourself in these questions. Okay. All right, well, let's move on to the next topic. And that's the topic of C13 NMR. C13 NMR. Okay? So, in this kind of NMR, what kind of atoms do you think we'll be looking at now? Carbon. Carbon. Okay, so we're going to have to shift our focus. We've been used to looking at hydrogens. Now we want to look at carbon atoms. Okay? So now we want to focus on the carbon atoms in the molecule. Well, there are 2 major types of carbon atoms. The two major types are carbon 12 and carbon 13. What are those two carbons called of each other? They are called what? Isotopes, where they differ by a neutron. Okay? So C13 has an extra neutron, so its mass is a little heavier than carbon 12. Okay? If you look on the periodic table, which of these two does the periodic table say that we have? Carbon 12. Carbon 12. Okay? So which of these two do you think is the most abundant in all of our molecules? Carbon 12. Okay? So carbon 12 is the most abundant. Okay? In fact, if you were to use percentages, about 99% of all carbon atoms are carbon 12, and about 1% are carbon 13. Okay? There is another isotope, carbon 14, that's a very, very small fraction that's out there, so we'll just ignore it. All right, so that's one difference between the two isotopes. Another difference, which is probably the more critical difference, is that carbon 12 has no spin, but carbon 13 does have spin. Okay? So what do you think the significance of that is? Yeah. So which one do you think is NMR active? Carbon 13. Okay. Carbon 12, we cannot do NMR because it doesn't have spin. Okay, so we discovered that on the first lecture of NMR some time ago. Okay, so let's see the significance of that. Let's draw out this molecule here. Two chlorobutane. Okay. And again, we're going to look at the carbon atoms in this molecule. Okay. So let's come and look at this one. That's CH3. And let's suppose that that particular carbon of that particular molecule turned out to be a C13 molecule or atom. Okay? Based on these percentages, what is the percent probability that that would be a C13? No, wouldn't be. There's only 1% or C13. In fact, none of these others, in all probability, would be C13. Okay? What about if I found another molecule where that CH2 was a C13? What might you say about the others? That they probably would not be C13 either. Okay? Because of the low probability. Okay? So this abundance is coming into play up here. Okay? So we get two facts from this little study here. Okay? One fact is what? Well, if I did C13 NMR, what would I predict my signal to look like? A doublet? Triplet? What do you think it might look like? Well, if I'm looking at this carbon and its neighboring carbon, so if it's being split by this carbon, but that carbon is not NMR active, so N would be then what? 0. So that should look like what? A singlet. Okay? So the signals will be singlets. That's nice, isn't it? I don't have to worry about looking at all that splitting. Okay. So that's one fact we can take away from this. Let's look at a second fact. Okay. If you look, no one molecule will give you all of the carbon-13, all the carbons to be carbon-13. Okay? So what does that tell you? Well, I need a lot of these molecules, or very few of them, to make sure I get C13s throughout the molecule.
A lot.
Yeah, I'll need a lot of them. I'll need a jillion of them, okay? As many as I can. So, in other words, I will need a high concentration of sample to ensure I get C13s throughout the molecule, okay? Because again, no one molecule gives me them all, so I need a huge collection to do that, okay? What about if we were doing hydrogen NMR? Do I need a large concentration for those? Why not? Because all the hydrogens are what? NMR active. So I don't need a high concentration. In fact, I could do it on one molecule if I could isolate one. Okay? So for hydrogen NMR, we use a very low concentration of sample. Okay? If you did a high concentration, then you would saturate your NMR instrument and you would get kind of a messy spectrum. Okay? You get peaks real high and everything. Okay? But for C13, I can make it, and I can make it, and I want it as concentrated as possible. Okay? So I just keep stuffing sample into solution. Okay? So when we say a high concentration, that means we also have a solvent, and that solvent is deuterated chloroform. Okay, that we write as CdCl3. Okay, so this stands for deuterated chloroform. Okay, that's the solvent that we dissolve our sample in, whether it's hydrogen NMR or C13 NMR. Okay. The reason for the deuterium is in hydrogen NMR, deuterium does not show a signal. You see that? Why would I want to see a signal for my chloroform? Because that's the solvent. I don't care about that. I already know what it is. I'm just concerned with what that is. So I want my solvent to be invisible. So that's why I use deuterated chloroform. Okay? And there's other deuterated solvents out there that can be used, but this is the most popular one you would use in the lab. Okay? And for C13, there's only one carbon there. Okay? And that carbon atom you will see in C13, okay? And that will usually show up at 78 parts per million for C13. So why don't you go ahead and take your handout, pull it out here. And look at the front page at the bottom. And you'll see your first C13 NMR. Okay? If you look at the box, you'll see two spectra. Just look at the bottom one for now. Okay? Look at the chemical shift values. What do the chemical shift values range from? Where's yours? Did you get one last time? Okay, so you can see it's a broader scale, isn't it? From 0 all the way down to 240. Okay, that's the first big difference. You guys all ready to go?
I'm gonna do that.
Told you to be bringing them to every class. The scale goes between 0 to 240, so it's a much longer spectrum, okay, than hydrogen NMR. Okay, let's go ahead and look at the molecule that it gives us there. So here's the molecule we want to investigate. And if you look at this, we're just looking at the carbon atoms. There's no plane of symmetry, is there? So how many different signals for carbon should I see? 4. 1, 2, 3, and 4. See, that one doesn't have any hydrogen, so I don't care. I'm looking at the carbons. Okay, so we call that A, B, C, and D. Look at the carbon atoms. See, some of you already got tripped up. Which of these carbons should be the most downfield?
B.
B, look at that, right on that oxygen, B shielded. Okay? And in fact, it is. Here it's showing up at about 210 or so. Okay? So this will be B. In fact, we can make a nice little statement here that carbonyls show up anywhere between 180 to 240. Okay? That's nice data to know. Okay? So even IR told me I had a carbonyl at 1700. Okay? What would be the most upfield peak?
D.
D, furthest from the D shield. Okay, and then what would be the next upfield, A or C? A, more hydrogens. And then C. Okay, so that still works in C13 just like it did in hydrogen. Okay, so any questions on that one? Okay, not too bad, is it? Since we kind of have Proton NMR under somewhat control, okay? Told you this would be easy as long as you have the other master, okay? You'll see it, if you see the other spectrum right above it, okay? We'll come to that next time and see what's going on with that one, okay? Let's turn the page, okay? Go to this one here. Okay. So this one here is the same molecule we just looked at. See that? But here I wanted you to see something. You see the peak, the carbonyl peak? What's it saying the carbonyl peak shown as? 207. But is 207 on the spectrum? No, it stops at 200. Okay? So here, this is what's called an offset peak. An offset peak, where they bring a peak that was off the spectrum, more downfield than I'm showing, and it brings it on, and it gives you the value right above it, okay? So here it gave you exactly where it's showing 207, okay? So that's an offset peak, and they're just trying to help you because they chopped the thing off at 200, okay? Notice too, you still see a TMS peak. Remember TMS had 4 CH3s, so you're seeing the carbon of those CH3s, okay? Let's go to the bottom spectrum, okay? And see if we can start labeling those carbons.
I have a quick question.
Yeah.
Why is C more downfield than A?
Okay, CH2s are more downfield than CH3. Remember that rule? The fewer the hydrogens, the more downfield it is. Okay? So, the reasoning for that, these hydrogens tend to act as shielders, so as I take them off, it makes it more downfield. Okay, let's look at the other molecule here. Acetophenone. And let me draw the C13 it's giving us. So there's a rough sketch. Okay, let's figure out what's going on here. Okay. So this 195 peak, that's obviously what? A carbonyl carbon. Okay, always stands out down there. Well, let's figure out the other peaks. First of all, let's ask, is there a plane of symmetry in this molecule? Okay, students always say no, but there is one. Okay, it's right here. Okay, say why, how could that be one? What happens is this bond is rotating very quickly. So this oxygen averages out the same time there as down here. Okay, so I can draw a mirror plane right there. Okay, so something to keep in mind. That bond rotation can average that oxygen out. So that gives me an A, a B, a C, a D, an E, and an F. See that? So these two are the same as these two. So I'm predicting I should get how many peaks? 6 peaks. Did I see 6 peaks?
No.
No, I see 5 peaks. So let's see what's going on. Okay? What's the peak at about 25? Give me 11. A. Okay. Benzene carbons, remember benzene de-shielder. Benzene carbons always show between 120 and 140. Okay? Just like in Proton NMR, they show between 7 and 8. Here's the signature on C13, 120 to 140. Okay? So let's identify these. C, benzene carbon, is closest to the de-shielder, so that should be the most downfield one there. D is the next closest to the de-shielder, so that should be that one there. Okay. But now I have 1 peak left. Well, what must be going on are E and F are far enough away from this de-shielder that they basically overlap. I couldn't have predicted that, but the spectrum is telling me that. Okay? So E and F are represented by that peak. That's making sense because that peak is twice as tall. Okay? And then the B peak is that carbonyl down there. Okay? Any questions on how we did that one? Okay? So you can see the only difference is the way the signals look like, all singlets, and we got different chemical shift values that we got to get used to, a lot higher. But the principle's still the same. Shielding, de-shielding, okay, upfield, downfield. Okay. Yeah.
And you knew that A was CH3 and then a particular range for CH3 or just because
Yeah, typically these will show up around 10, but since it's on the carbonyl, it's a little bit shielded there. Okay, but yeah, they're typically 30 and below. Okay, and then CH2s and CHs a little bit higher. Okay. Whereas on Proton NMR, they were what, around 1. Okay. And then when I put these shielders next to them, it gets a little higher, 2 or even 3 or even 4. Any other questions? Okay, well, let's stop there for today and practice this homework, and we'll come back on Friday.